Okay.
Thank you very much.
Okay. Thanks for the introduction. And in the following about 1 hour, I will show some detailed calculations of this Lagrangian and how to use it to do some explicit calculations. So, for example, pi scattering. And first, let's do this. Let's do this how this equation holds. And first, let's look at the field U. U is defined in the last line. We can just copy it here. So is it clear enough? Or I should write it larger? Okay, okay. So it's just so here f pi is just a constant. It's called the pound decay constant. So and phi is a field of the pseudoscalar, and the tau is just the Pauli matrix in the isospin space. And then what we need to do is to look at the Lagrangian. It's in the next page. Okay. Trace, I will use this symbol to stand for the trace. It's partial mu u, partial mu u dagger. Okay. So obviously we need to expand it because it's an exponential. We should expand it at the original point, and it should goes like this. So it's simple. 1 plus I phi dot tau of f pi plus 1 over 2 f pi I square. So phi dot tau square. And blah, 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 blah. So everyone knows it. And again, we should do the derivative. That means the partial mu u should equal to, so it's a constant. So this one vanish, and again, in the following is f prime I tau dot partial mu phi plus dot phi times tau dot partial mu phi and another term. And blah, blah, blah. Something like this. So here we should pay attention that these two terms we should write it separately, because here's the tau matrix, and these two is not equal because tau matrix is not communicate. And so similarly, partial mu u dagger should equal to, so this one we just add minus sign, and this one is plus, and again the next term should be minus, plus, blah, blah, like this. So what we need to do is just to put these two terms inside these trees. And so this constant is here. And when we put these two terms into these trees, we should actually we should expand this Lagrangian term order by order. So we can see the first, the lowest order in terms of phi is 2, right? So at the order of, yeah. So at the order of O, order of phi square. So it includes this one and the corresponding term here, right? I should write it down. And it's tau times partial mu phi. So the only possible one is these two, right? So it should be square. It is f pi square 1. We take the trace tau times partial mu phi and tau times partial mu phi to this one. Okay, now how to do the trace? So tau is just the Pauli matrix, and we know that the Pauli matrix have some properties. For example, we know that the trace tau I should equal to 0 because the Pauli matrix is traceless, and also tau I tau j equal to 2 delta ij. And let's also we need the 4 Pauli matrix later. It's dot ij dot kl minus dot ik dot jl plus dot il dot jk, like this. So it's you can find such relations on the website everywhere. You can find it. So because the key point is that how to derive this one is not very hard. So the key is this one. 2 Pauli matrix, they multiply it equals to delta ij identity matrix and ijk sigma k. So I don't remember whether it's plus or minus anyway. So it's maybe plus or minus, you can check it. Just put this one into these trees, you can get these relations. So use these relations. What we need to so far is just this one, because for this one we can write it as tau I tau j trace partial mu phi I phi j. Okay, so this one is just 2 delta ij, and then we have partial mu phi I, partial mu phi I. So it's just the first term here. So this one is relatively not so complicated. So if you have any problems, you can stop me to discuss. So let's go to the next order. For the next order, we should have, of course, we should phi 3. Let's see what happens for phi 2, 3. And if we want to look at this order, we should expand the u to the next order. So we have the partial u, partial mu u equals to the above one plus again, we should pay attention to the order of such field. This one term and plus tau phi tau partial mu phi and tau phi. Again, the last term is and for the partial mu u dagger, just add a minus sign to this. So to this order, we have what we can have. Oh no, to this order we doesn't need this, but to the next one we need this. So just put it here, and for phi 3 we should have this times this one, and also this times this one, and this times this one, right? This factor we just copy them. And f pi I tau partial mu phi times this one. This one is so here should be a minus sign. And the other fields. And then we take the trees and plus this times this. So let's look at the above one. We the what enters the trace is just this and this. So here, for simplicity, we have this one and phi I, phi partial mu, phi j, partial mu, phi k, blah blah like this. We know that this one is just proportional to epsilon ijk is anti-symmetry to each index. And also we can see that here we have some symmetric component. So we will always have 0 for such term. Yeah? Mm-hmm. Yeah, of course, yes. Yeah, yeah, of course. Yes, so that's why I read this term so ugly, because I will erase it. Okay, now let's go to the next order. So to this order, we have several different contributions. One is that we can use this phi squared and times the phi squared in the U dagger. So we'll have square. Because this is, we can just add a square here. And we expand it, it's tau dot phi. We should have 4 terms, but it can be divided into two components. One is phi and again itself. And this one. And also so we have such 4 terms, and because they are in the trees, right? So for the trees, we can put which one? Okay, this one. We can put this one at the beginning, so it's square, and also this one is square. No, tau. Okay, also this two is square, and this two is square. So these two are the same. We just put factor 2. And similarly, these two are the same. Something like this. And then we can take the trace. And another term should be this order, this phi in U and the phi cubic in U dagger. Okay. So we have another contribution. Okay, it's 6. Okay. And we just put everything into the trees. Mu phi times that. Okay, times these three terms here. So again, we can using the similar trick like this. We can combine the two of them into one, and finally we have tau. Okay. We have this one, and 2 times of tau partial mu phi square, tau dot phi square. Okay, so this go to this two term. Here we should have a minus sign here. Because this is plus, but for this one is minus. So we have an additional minus sign here. So we need to add these two contributions, and for example, all the prefactors we can leave it alone, and what matters is that So for short, this one I will just use this notation and plus 2 tau dot phi square tau mu phi square and minus okay. Okay. For this term we have one. Okay. Again, there we should have a factor 2 because we have such two contributions. I left it. I missed it. So here we should be 2 and okay, it's 1, 2. So it should be 1/3. So this one is 1/6. This one is minus 1/6. So what we have totally is and now we are going to take the trace for these two terms. Okay. Just see this example. We want to calculate the trace of this term, and we just write the matrix in the trace and other fields I, J, K, L. And this four polymetrics, the trace of it, we just write down its expression. So it's several terms of delta. And we just contract this index with this field, we can simply get the result. This one dot phi dot phi times these two dot phi minus this one dot this one and this one dot this one plus this one dot this one and this one dot this one. So we just add 2 here. And similarly, for this term, we can get the result as this one. Okay, just write down the result. Only one term. So have these two results and take them into this expression. We can directly get what right here. Here, it's just our final destination. So for now, is there any question? Or is that clear to you? Okay, now let's move to the calculation of pi-pi scattering. So where is the pion field? Okay. So the pseudoscalar matrix, take this one, and we can directly write down the component of the phi. So phi, take this one, and we insert the phi into the Lagrangian. Here, we can express the Lagrangian in terms of pion fields. So, for example, what the building block contains this one, we can calculate it as this. Just use this one. Also, the phi dot partial mu phi goes like this, and of course similarly just put partial here. Blah, 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 blah. And now take these expressions into this one. And what we want to do is that, of course, if we take all of these into this, we get many terms. But what we want to do is to calculate the pi plus pi 0 to pi plus pi 0 is for this process. So make our life easier, we can just pick up all the terms contains just these 4 fields. Other terms we can just ignore them. So the relevant terms are and for the next one, okay. So if we want to calculate the scattering amplitude, and for the first contribution, and we just do the wave contraction to get the amplitude. Like, for example, this term, we should have the momentum of the pi 0 and pi 0 here. So what we have is 2, and also there's a symmetry factor 2 because the pi 0 can contract with this one or this one. So this 2 is from here. And pi 0 and pi 0, 1 is income and 1 is outgoing. So it's income minus p. For example, we make this convention is pi plus pi 0, pi plus pi 0, and its momentum is p plus prime, p0 prime. Okay. So for the incoming pi 0 is this one. For the outgoing is this one. Also, this term contributes to the momentum of pi plus momentum. So this one is just p0 dot p0 prime. And this is p plus dot p plus prime. Because the final expression is in terms of the Mendelssohn variable t is defined as p prime minus p squared. So we know that this one is equal to p0 squared plus p0 prime squared, and no, it's p0 minus p0 prime squared minus p0 squared minus p0 prime squared over 2. This one. And this is just exactly t. P0 squared, because up to now the pound is massless. So these two all equal to 0. So finally it's just a t over 2 system and t over 2. So in total, it's 2t, 4t. The next contribution is this one. Here's a 2, this one. And we have, this is the outgoing pion. So it's IP plus prime minus this one IP plus. Okay. And this one, it also has two possibilities. One is pi0 contract with the incoming, and another is contract with outgoing. And also we have the IP0 prime minus IP0. So we take the I here, and this one. these two, because we have P plus P0 equals to P plus prime plus P0 prime. And we exchange them. So these two just give the minus 2t. So it's 2t. So these two contributions add together, we have 60. And maybe I lost some factors. Here is 6. Here is 60. So these two cancels. And in short, it's proportional to t, but there's maybe some missing minus or missing some factors. But in short, the strategy is just what I showed. So you can, if you are interested or in the future you need some such problem, you can do as this with being more carefully. Yes. So, okay. So, do you have any problem with this? If no, I will go to the next, the short one. Okay, yesterday, Professor Nevis showed that this term and also this term is carry invariant. That means under carry transformation, these two terms keeps unchanged. So there's the last term, we want also know that it is carry invariant. But this is not complicated. Is so and the carry transformation, this math field psi goes to, for example, let's take the vector one as g v psi. Okay, just here. And psi bar goes to, okay, psi bar is psi dagger gamma 0. So it goes to GV psi. We take a dagger gamma 0. It's okay. It's just a psi bar GV dagger. And sigma tilde is just some combinations of sigma and sigma dagger. Okay, it doesn't matter what's the form. It's a linear combination. So we know that sigma and the Carroll transformation. Okay, here. Okay, sigma is just a u. U transform like this. Again, sigma dagger transform like this. So what we want to know is this one. And it's just some combination of this and this. So this one will change to GV dagger is GV sigma, GV dagger, and this is GV percent. So all of them cancel. Similarly, for the second term, it's the same. So this one, of course, is carry environment. So that's what we want to talk today, and maybe it's a good time to take a break, and then Professor Nevis will continue the following uh, the following discussions on the Carroll Lagrangian. Okay, thank you.